Today, we're going to jump in a time machine and go way back to the dawn of the deep learning revolution. We're going to look at one of the OG neural networks that first taught a computer how to actually see. Yep, we're talking about the legendary LeNet-5, an architecture that literally laid the foundation for how computers see our world today. I mean, think about it for a second. This is the big question that kept AI researchers up at night for decades. It's one thing for a computer to just crunch numbers, right? But how do you get it to look at a picture, which is really just a chaotic jumble of pixels, and recognize something as simple as a handwritten number? Well, LeNet-5 was one of the very first and most successful answers to that question. It was created by the brilliant Yann LeCun way back in 1998. And its mission, while it sounds specific, was a huge deal. Teach a machine to read handwritten digits. You know, like the kind you'd find on a bank check. So what was the magic trick? How did it actually work? Before we do a full tour of the network, layer by layer, we need to get a handle on the core ideas that made LeNet-5 so groundbreaking. These concepts are, and I'm not exaggerating, the absolute bedrock of modern computer vision. The genius of LeNet-5 really boils down to a few brilliant and kind of intuitive ideas. First, you've got local receptive fields. This just means that instead of trying to look at the whole image at once, the network's little workers, its neurons, only focus on tiny patches. Then there's shared weights. Now, this is cool. Imagine you have a special magnifying glass for finding, say, a straight line. Instead of having thousands of different magnifying glasses, you just slide that one across the entire image. That's what this does. And finally, you have pooling layers, which are just a super clever way to shrink the image, keeping all the important bits and tossing out the noise. It's a masterclass in efficiency. Okay, got those core ideas locked in? Good. Now, let's actually take a walk through the network itself. We're going to follow a single lonely image as it gets processed, squished, transformed, and finally understood by LeNet-5. You can think of this whole thing like a high-tech assembly line for recognition. A picture of a handwritten number gets plopped in at the start. First, it gets scanned for really simple stuff. Then it gets shrunk down. Then it gets scanned again, this time for more complicated patterns, and, you guessed it, shrunk down again. Finally, the last few layers act like a little committee that looks at all the evidence and makes the final decision. So step one is all about finding the most basic building blocks of any number. We're talking about the absolute fundamentals. Horizontal lines, vertical lines, curves, little corners. The network has to learn to see these things first before it has any hope of seeing the whole picture. And this is how it does it. That first convolutional layer, C1, is basically a team of scanners. It creates 6 different feature maps. You can think of them as 6 little detectives, and each one is on the lookout for a specific kind of edge or curve. Right after that, the S2 pooling layer swoops in and very smartly shrinks the image in half, basically condensing the notes from our 6 detectives without losing anything important. Okay, so the network has found a bunch of simple lines and curves. Now what? Well, the next layers start putting those pieces together. It's like, hey, this curve plus this straight line, that could be the top of a 2. Or, these 2 circles together look a lot like an 8. This is where simple shapes start turning into actual recognizable patterns. So at this stage, the C3 layer basically says, we need more detectives. It expands the search party from 6 to 16 different feature maps. It's now hunting for much more complex combinations of the simple features we found earlier. Then, another pooling layer, S4, shrinks the map again, boiling everything down into a tiny, dense package of pure information. And here we are, the final stages. All the visual evidence has been collected, condensed, and distilled. These last layers aren't even looking at pixels anymore. They're looking at the patterns that have been detected. Their job is to weigh all that evidence and make the final call. This is a moment of truth. This table shows the grand finale. The C5 and F6 layers take all that rich pattern data and just funnel it down from 120 neurons to 84 and then finally to just 10 output neurons. And each one of those 10 neurons represents a vote for a digit from 0 to 9. The neuron that screams the loudest wins, and that, my friends, becomes the network's final guess. So we've seen the blueprint, the elegant design from 1998. Now for the really cool part. Let's connect that abstract idea directly to the modern code that actually brings it to life. Okay, here's that full architecture one last time. Just burn that pattern into your brain. Conv, pool, and then the final decision layers. Got it? All right, let's see the code. And there it is, that blueprint we just spent all this time dissecting, translated into Python. This little snippet, using the super popular PyTorch library, builds the exact LeNet-5 architecture. It's just a perfect, clean translation of LeCun's vision into a language that a computer can run. Let's break it down real quick. See that first line, conv2d? That is our C1 layer. The numbers 1, 6 are literally telling it, take our one grayscale image and create those 6 detective feature maps. And the next line, av pool2d, that's a direct command to build our S2 pooling layer. It's a perfect one-to-one match. And the beautiful pattern just keeps going. The next conv2d line, that's our C3 layer, taking the 6 channels from before and blowing them up to 16 to find those more complex patterns. And right after that, you see the S4 pooling layer, ready to do its shrinking job once more. This is literally theory turning into reality, right on the screen. And to wrap it all up, here's the code for our final decision layers. The C5 convolution creates 120 feature maps, and then the first linear layer, that's just code for a fully connected layer, takes those 120 features and funnels them down to 84. It's just amazing how a concept from a 1998 research paper translates so cleanly to a piece of software you can run today. Okay, so this has been a really cool history lesson, but you might be thinking, why are we talking about an architecture from 1998 in a world of super advanced AI? Well, because its impact is absolutely massive and you can still feel its shockwaves today. This right here is the whole ballgame. LeNet-5 didn't just solve a single problem. It created this standard recipe, the go-to playbook for image classification. This pattern, convolution, then pooling, then the final classification, became the fundamental blueprint for pretty much every computer vision model that came after it. Modern networks really are its direct descendants. You can think of it like a classic Ford Model T versus a new Tesla. The core design is kind of the same, but every single part has been upgraded. We've swapped out the old activation function for the much faster ReLU. We've replaced simple average pooling with the more effective max pooling, which is better at finding the most important features. And we've added all sorts of new tricks like Dropout to make the models more robust. And that's why LeNet-5 is still so important. It's the perfect model to learn with because it's so small and elegant you can actually understand what every single layer is doing. It's not some black box. It is, without a doubt, the grandfather of modern visual AI. And if you understand LeNet-5, you understand the very foundation of everything from the Face ID on your phone to the computer vision in self-driving cars. LeNet-5 proved that a computer could be taught to see, and it took more than 2 decades for that foundational idea to grow into the mind-blowing AI we have today. So it really makes you wonder, what fundamental breakthrough is happening in a lab right now that's going to completely define the world of, say, 2048? What's next?